Welcome to another video in the PowerPoint series from movingelectrons.com, and our topic for today is going to be fault current analysis. We're going to be focusing on a three-phase fault, and this is the maximum fault level that a system sees. It is rare in practical day-to-day that you'll see a three-phase fault occurring, but it is the maximum value and it has that significance when you're sizing your equipment and so on. So let's get right into the question. Calculate the three-phase short circuit value for the system shown at the load bus. So this is our system. We have a source, which is the generator. We have a transformer and we have a transmission line. That's the load there, and we've been asked to find the fault current here at the load bus. The generator is a 10 MVA generator operating at 13.8 kV, and that's the impedance value there. We have a transformer, which is a 12 MVA transformer. It has a voltage ratio of 13.8 to 4.16 kV, and that's the impedance level 8.5%. The transmission line is operating at 4.16 kV. It's a 10-mile long line, and that's the impedance values, the resistance and the reactance values there. The three-phase short circuit current is most nearly, and these are the values we've been given. So finding out these three-phase short circuit value, it has a couple of steps involved. So we'll get right into the solution as soon as we see the formula here. This is the primary formula we'll be using. So this is the short circuit current that we've been asked to find is given by the base current at where the fault is occurring. So we'll see the base current here divided by the per unit impedance. That's the impedance of the system all the way from the source of the fault to the fault. So here we'll see what we'll do is we'll draw an impedance diagram, and I'll get into that in the solution. That's one of the steps that we do. Before we get into the impedance diagram though, we have to convert. One thing you'll notice here is the impedances are given, but they're all given at different bases. For example, for the generator, you have a 10 MVA base. For the transformer, you have a 12 MVA base. The voltage bases are different as well. The transmission line is operating at 4160 volts or 4.16 kV. So the very first step that we do when solving our problem, and I'm going to summarize, there are four steps that we're going to do. I'm going to summarize those at the end. So the very first step that we do is we convert all impedance values to a common base. So let's define system bases here. Let's say our power base, S base, is going to be what the generator base is. So that's 10 MVA. What's going to be our voltage base? Now, whenever we have a transformer, we have two sets of circuits. So you have circuit 1 here, which is the primary circuit, and you have circuit 2 here, which is the secondary side of the circuit. So what happens generally is you have the transformer on the primary side and you have a transformer on the secondary side. So you have a different voltage base here and a different voltage base here. The power base remains the same across the primary and the secondary side. So generally it's a good practice to define on the primary side the voltage base as being the primary voltage of the transformer, and on the secondary voltage of the transformer. So let's go ahead and do that. So let's say our voltage base 1 is going to be 13.8 kV and our voltage base 2 is going to be 4.16 kV. So we've defined our bases for the system. Now let's start converting the impedance levels for all of these different components, the generator, the transformer, and the transmission line, to this common base. So let's look at the generator first. So the generator, we've been given the transient reactance as being 18%. This is already at a base of 10 MVA and 13.8 kV. It's on the primary side of the circuit. So we can just straight away write that as 0.18 per unit. Let's look at the transformer. We've been given an impedance. This impedance we're going to assume is primarily going to be inductive impedance. So we're going to write that at XTX is 8.5% or 0.085 per unit. But we have to remember that this is at a 12 MVA base. So that's a 12 MVA base and 13.8 kV. So that's the power and voltage basis for that particular, for the transformer impedance that's been given. So let's convert this, and we're going to convert this using this formula. That's the reason I've mentioned these two formulas, and I'll deal with this as well once we come to that. But this one here, what we say here is, if we want to convert an impedance to a new impedance basis, so the Z per unit new is equal to Z per unit old multiplied by your kV base old basis over kV base new, the square of that, multiplied by the MVA base new over the MVA base old. So in our case, the kVA base remains the same. The old base is 13.8 kV, which is where this is defined at. The new base, we want to convert it to and the new base we've defined for this system is also going to be 13.8 kV. So this is going to cancel each other out, and we're going to get 1. So we can ignore this portion. The MVA base new is going to be 10 MVA. The MVA base old is going to be 12 MVA. We've been given the value at 12 MVA. We want to try and convert it to 10 MVA. So I hope that's clear. So let's go ahead and do that. So you're going to get the Z per unit. In this case, new is going to be, old one is 0.085. I already said the KVs are going to cancel out. So what you're going to have is, in the numerator, the new basis you want is 10 MVA over 12 MVA, and you're going to get a value of 0.07 per unit. That's your new XTX at 10 MVA and 13.8 kV as the basis. So we've converted this. Now let's look at the transmission line. So the transmission line has two components. We've been given the resistance 0.01 and the reactance 0.24. Now the other thing to notice here is these values. I think what's not mentioned here is this is in ohms per 1,000 feet. So we have, and the line is 10 miles long. So the way to convert an ohmic value into a per unit value is, your Z per unit is the Z actual over your Z basis, and Z basis is nothing but kVA base square times MVA base. This is all from your per unit theory. So if we substitute this in the denominator here, this is what you'll get. You'll get a Z actual, which is the ohmic value that you've been given, times your MVA base over your kV base square. Now this is in circuit 2, the transmission line is in circuit 2. So your MVA base here, the MVA base remains the same. So this remains to be 10 MVA. Your kV base becomes 4.16 kV. Your Z actual now is this ohm per 1,000 feet. But the one thing we have to consider is, if we are assuming that the impedance value is evenly distributed through the transmission line, we have to multiply it by 10 miles. So the one unit conversion you'll have to remember is that 1 mile is equal to 5280 feet. So let's use this information and convert. First, let's look at the reactance of the transmission line is 0.24. So that's 0.24 ohms per 1,000 feet, and you have 10 miles times 5280. So this is what we're using to convert here. Times, you convert 10 miles into the feet to cancel the feet out. I hope that's clear. And so that's your Z actual in essence. And then you're multiplying it by your MVA base over your kV base square. So you'll have 10 over 4.16 square. And when you calculate this value, you should get 7.3 per unit. Similarly, your resistance value, so this is in per unit, this is per unit, should be 0.01 per 1,000 feet times 10 miles of the line times 5280 to convert it into feet times 10 MVA over 4.16 kV square, and this should give you a value of 0.31 per unit. As I always encourage you to do double check these calculations. It's quite easy to go wrong in them. I have checked them myself, so I'm hoping there is no mistakes, but if there are, please do let me know. So now what we've done here, we've converted all our impedance values to the common bases. So we've converted our generator, we have our transformer, and we have our transmission line. So our step two is going to be to calculate the system impedance. So to calculate the system impedance, what we can do is we draw what we call an impedance diagram. So let me go ahead and draw that very quickly. So this is where we are starting off. This is our generator impedance. Then we go forward and then we come across our transformer impedance. Then we move forward, we come across our transmission line resistance value and our transmission line reactance value, and that is the load bus, and this is where we have the fault. So we found this to be 0.18, that was 18%, so that's 0.18 pu. This we found out to be 0.07 pu, this was 0.31 pu, and this is 7.3 pu. That's our fault. So what we do is we find out the system impedance all the way till the fault from the generator. Once we have that value, we will have the denominator here for our short circuit current. So the impedance values, be careful, this is resistance, the rest of them are reactances. We cannot just simply go ahead and add them to calculate our system impedance. We have to first find out our reactance, which is 0.18 plus 0.07 plus 7.3 should give me something like 7.55 per unit, and then my resistance, I only have one resistance value, it is 0.31 pu. So what is my impedance? It is x square plus r square under root. So if I calculate that, I will get a value of 7.56 pu. This is my impedance. Be careful, do not just algebraically add all these values. Again, you see here the reactance hardly, the resistance of the transmission line hardly has an effect on the overall impedance. But since we were given the value, we've gone ahead and used that. Now that we have calculated our system impedance, let's move ahead to our step 3. Our step 3 is going to be calculate the I base. So our fault occurs in this area in circuit number 2. So our voltage base here was 4.16, our power base was 10 MVA. So our current base is going to be S base over root 3, because this is a three-phase system, times voltage base. So we have 10 over root 3. This is MVA. So we can say 10 times 10 to the power 6. And this is 4160. And you'll get, because it's 4.16 kV, so then you get a value of 1387 amps. So now you have your values to plug in into your short circuit current formula, which is I base over Z per unit. So let's look at that. That's 1387 amps over 7.56 per unit should give you a value of 183.6 amps. Oops. Let's see if let me just cancel that. 183.6 amps. There you go. That's better. Let's see if that's one of the. There you go. That's option number A. That's one of the choices we've been given. So that's how we go ahead and solve that a fault analysis problem, a three-phase fault analysis. What I'm going to do is I'm going to summarize the steps for you. So the steps are as follows. You have step 1 is where you convert all impedances to a common base. Step That's step one. Step two is you calculate your system impedance. Step three is you calculate your I base. And then step four, so this is Z per unit is what you get. And then here is what you calculate. Your final step is calculating the short circuit current I base over Z per unit. So those are the steps to find out the three-phase fault current. Since we have a couple of minutes, what I'm going to do is I'm going to quickly show you where we get this formula from, where we can derive that. It's got nothing to do with the problem, but just want to give you a little bit of a background so it helps you understand that a little bit better. Let's say this is our system. This is where the fault is occurring. If we draw this out, so this is your impedance at the short circuit at the time when the short circuit occurs. This is your voltage at the instance when your short circuit fault occurs, and that's your short circuit current, which is what we've been asked to find out. From Ohm's law, what we can say is, now this is the total system impedance here, okay? We can say that that's the voltage at the time of short circuit over the impedance during short circuit. So that let that be equation 1. Um, what we also know now is our Z per unit. So let's find out Z per unit during the time when the short circuit occurs. It's going to be Z short circuit, because that's an ohmic value, over your Z basis. We know Z basis is actually nothing but voltage base over your current base. So what is your now if we substitute this in this equation right here, then we get Z per unit is equal to I base times Z short circuit over your voltage base. We can write this as voltage base over Z short circuit is equal to I base over Z per unit. Correct? We just take this there and this portion there, this down here, and that's what you get. Now let this be equation 2. If voltage base is equal to voltage short circuit, what does equation 2 become? Equation 2 becomes voltage short circuit over Z short circuit is equal to I basis over Z per unit. And this from equation 1 is nothing but I short circuit. So that implies that I short circuit is I basis over Z per unit. And this is true because during the short circuit, whenever the short circuit occurs, for example, in this case, when the short circuit did, sorry about that, when the short circuit did occur, the voltage is still going to be 4.16 kV, right? And that's the voltage basis. So when the voltage base is equal to the voltage short circuit, this is the value that you get, and that's where this formula comes in that we use in calculating the short circuit current. So that was just a little side note. It's got nothing to do with solving the problem. I hope you still makes it a little bit clearer where we get that equation. If you have any questions, feel free to send me an email at nimish@movingelectrons.com. Let me leave you with a sample problem. So what I'm going to do is I'm going to draw out a system here. So let's say this is a 2-generator system. Both the generators are operating at, let's say, 13.8 kV. So this is connected to a 13.8 kV bus. You have a transformer here, and let's say that's directly connected to a load. There's no transmission line. What I'm anyways going to do is you're going to find out the fault at this level. So the fault's a lot closer to the source. What you've noticed here is the total impedance of the system matters from the source all the way till the fault. So if this fault was here, the fault level would have been much higher because the system impedance is a lot lower. So the higher the system impedance, the lower the short circuit current. So in this case, the fault I've said occurs a lot closer to the generators. Now the values, let's say this is a 10 MVA with an impedance level of, let's say, 18%. This is a 15 MVA generator with an impedance level of, let's say, 20%. This is a transformer, which is a 20 MVA transformer. It's 13.8 kV on the primary. Let's say it's 480 volts on the secondary. And you have an impedance level of 10%. So find out this fault. I think I have given you all the values that you need. This is not 75, this is 15 MVA. Leave your answers in the comment section below, or if you have any problem solving this, or if you have any problems understanding that, or any feedback about what we discussed today, leave that in the comment section below. And till next time, good luck and have fun. Bye now.